Welcome to Calculus is Easy if you can relate it to the real world. And like the rest of mathematics, calculus is easy but also important and can be interesting because it tells you how the world works. Mathematics is training in disciplined thinking. The language of mathematics is precise. There is no wishful thinking, there's no hand waving. Errors in reasoning can be easily and unambiguously detected. Now, Calculus is Easy has 3 chapters. The first 2 chapters are basic calculus, and the third one has advanced topics in calculus. Now, these are not only the chapters, but this is also a roadmap. This is a roadmap for understanding calculus, and I'm going to refer to this roadmap again and again as we proceed. So, following our roadmap, we first arrive at chapter 1, and chapter 1 itself has different parts. And the roadmap for chapter 1 is that we are first going to look at mathematics in the real world. Then we shall come to integration. And what I shall show to you is that integration is really enhanced multiplication. So the idea behind integration is really no different from multiplication, but sometimes things are a bit more complicated, so you have to use the integral rather than straight multiplication. Similarly, differentiation is a form of division, and later what we shall see is that because integration is like a form of multiplication, enhanced multiplication, and differentiation division, so they are related to each other. They are kind of the inverse of each other. Now, the approach that I'm going to take in explaining calculus is going to be an informal approach. So I'm not really going to always be precise about what I'm doing. I've not always set up the correct axioms and build up from the axioms. Rather, I shall appeal more to your intuition about the real world. So this is like, what let's say an engineer would think. It's the way to understand the world, not exactly as a mathematician would go about it, but maybe an engineer would. So can we apply similar intuition to calculus as we had for multiplication and division? Well, calculus is actually multiplying little bits and then adding. So it's like a kind of an enhanced multiplication. Now, why would we want to multiply little bits? Because a lot of things in nature are not constant. So let me start with an example. And here, let's say you drive from Vegas to Los Angeles, and I ask you, so can you plot your travel? So you say, okay, if I was to plot my speed along the y-axis and time along the x-axis, then I took 4 hours to get to LA, and my speed was 72 hours. So I say, okay, your speed is 72 hours and you took 4 hours. So this is your plot of your speed versus time. And then I say, okay, 4 hours and 70 then would be, you traveled a total of 72 into 4 or 288 miles, right? So I say, okay, you traveled 288 miles, and then I say, I'm sure you did not actually travel at 72 miles for the entire stretch. That must be an approximation. You're just telling your average speed, but I want more accurate. I need more accuracy. So can you give me a more accurate description of your travel? Okay, so this is a very crude approximation. It's a very crude approximation describing how you traveled. And I want, I want greater accuracy. So for greater accuracy, let's say you give me a graph of your travel. You give me a speed, like your average speed for every half an hour. So you say, okay, the first half an hour, my average speed was 24.75. The next half an hour, it was 65.25. Then from 1 hour out to 1.5 hours, my average speed was 92.25. Then, I was in the middle of the highway. I really, it was the open road, and for the next hour, I drove at 105.75. And then I started slowing down. The next half hour, again, my average speed was back to 92.25. The half an hour after that, it was at 65.25. And then finally, the last half an hour again, it was 24.75. So I look at this plot, and the first thing I tell you is that, you should not be doing 105. That's way too fast. So I'm glad that nothing bad happened, and you're still, so don't do it again. And then I start calculating how much distance you traveled. So the first half an hour, I say, okay, your average speed was 24.75, and you traveled at that speed for half an hour. So I'm going to multiply this speed by this amount of time, which is half an hour, and I get 12.375. So the first half an hour, you traveled 12.375 miles. Okay. The next half an hour, I'm looking at half an hour, the next half an hour, and to get how much you traveled, the distance you traveled, it's going to be basically this rectangle, the area of this rectangle, that is this base, half an hour, multiplied by the speed, which is 62.25. So that is going to be 65.25 into half is going to be 32.625. So that's how much you travel the next half an hour. And I add these two. So the first hour you would have traveled, by adding these two, you would have traveled, when you add these two, you get 45. So for the first hour, you traveled 45 miles. Similarly, the next half an hour, you traveled at an average speed of 92.25. So for this rectangle, the height of the rectangle is 92.25, and of course the base is still half an hour. The distance that you would have traveled would have been 46.125 is traveled in this half an hour, and the total of these, so the total distance, this is the totals at the top, you add the amount you traveled in the first hour, which is 45, plus the amount you traveled in the next half an hour, which is 46.125, so you get 91.125. So that's your travel in the third half hour. Then for an hour, you travel at 105.75. So then the total, so now your base is 1 from 1.5 to 2.5. So this is 1, and the speed is 105.75. So the amount you traveled was 105.75 in that hour. And the total would have been 105.75 plus 91.125. So that would be 96.875, 196.8 0.875. And similarly, in this half an hour, you traveled 46.125. And then the next half an hour again, your speed was the same as this one. So you again traveled 32.625. And the final half hour, you traveled 12.375. And if I add all these, I get your total travel to be 288. Okay, you add all these up, you'll see that you'll end up at 288. This is the same as the previous total distance traveled, except that you've given me more information here. This is a more detailed information. Now I'm, kind of demanding, you can say, or like being a bit of a pain. And I say, no, this is still not accurate enough for me. I need precise. I need the precise speed for different points in time. These are still approximations. You're just giving me average speeds. I want the actual real speeds. And you say, okay, I actually traveled, I'm going to give you the speed. I actually traveled according to an equation. And the equation was that my speed at any point in time was equal to 108 into time minus 27 into time squared. So, okay, one thing which you note immediately is that when t is equal to 0, when you just start out, your speed is 0. At t equal to 4, at the end of your journey, 108 into 4 is 432, and 27 into 4 equal to 4. And the rest of the time, your speed kind of kept increasing, and then it went. Now, immediately note that this is what we call a continuous function. This was not a continuous function. This was kind of jumpy. At time half an hour, the speed was written as 24.75, but immediately afterwards, it became 65.25. So there was this like discrete jump from 24.75 to 65.25, and then from 65.25 there was a jump to 92.25. So if this is a function of speed with respect to time, we call this a discrete function. It's not a continuous function because it jumps. Okay, and the real world, things don't jump, or at least as long as you remain in classical mechanics, you don't get into quantum physics, things don't jump. And so this is much more like the real world. So for practical purposes, things don't jump in the real world. And so this is much more, this is like the real world, and this is what is called a continuous function. So what's a continuous function? What a continuous function is that at any point in time, the change is very little. It just changes, like just as the, time changes by little, the speed also changes by little. So speed then becomes a continuous function of time. So that's the idea of continuity, that the change in the function is very little when the change in the independent variable is very small. Okay, so they're both very small. So this is like accurate, and this is like the real world. However, I have a kind of a problem. I can't really calculate how much distance you traveled, because here the speed keeps changing. Over here it changed, but the number of changes, I still had only 1, 2, 3, 4, 5, 6, 7. I had 7 rectangles, but now it's continuous, so those rectangles aren't there anymore. So what do I do? If you give me this, like you give me this graph, and now this is real world, and I want to see how much distance you traveled. Basically what I'm trying to do is I'm trying to find the area under this curve as the distance, like it was here. It was the area of this rectangle plus the area of this rectangle plus this, and so on. So it was the area under this curve of speed and time. So distance was speed into time, and then each rectangle you had speed into time, and you calculated it and you added it up and you got the total distance traveled. But here also I would like this area under this triangle, not this triangle, this figure. It's actually a quadratic, comes from a quadratic equation. This function is a quadratic function of time. Now I want this area that so I want to multiply time by speed. My problem is that speed keeps changing, okay, and it changes like there are an infinite number of speeds here because it's continuously changing, and that's when you need integral calculus, because integral calculus will allow you to multiply speed and time even when speed continuously changes. So that is integral calculus. Okay, so let's see how integral calculus approaches this problem. What it says is that, okay, let's look at a particular point in time, like let's say, just pick an arbitrary point in time, let's say this is t. Okay, and then there is an associated speed which is st, right? So there's a point in time t, and there's an associated speed st. Now, just around this point in time, I take a little interval, and I call that little interval dt. Okay, so dt is the length of this little interval, and d is really, it's kind of short for delta, or it just like signifies a small change in t. Okay, so dt is a small change in t around this time t, and then I say, okay, if I look at this little interval of time, then I can assume, and this is a very important point in integral calculus, I can assume that the speed over this integral of time is constant. Now, if the speed is constant over this integral of time, then the amount of distance traveled in this integral of time would be the base, that is dt, into the speed st. Okay? Similarly, there would be another integral of time here, and there would be another interval of time here, there would be another interval of time here, there would be another interval of time here, and so on. And then the total area under this curve would be the summation of all these intervals. Okay, starting from the time when t was equal to 0. So starting from this point here, going all the way to t equal to 4. So the area under this curve could be found by, you don't have rectangles anymore, but these little intervals of time, because the change in speed in the, you look at the starting speed at the speed at the starting part of the interval and speed at the ending part of the interval, and because the interval of time is small, therefore the change in speed is also small, and therefore the speed can be approximated as, let's say, the starting speed or the midpoint speed or whatever. So, but some speed in this interval of time multiplied by the length of that interval is the area for that interval, and the total area is the sum of many such intervals, each of which of course have their different st. Like for example, when you are here, this is your st, so it will be different. When you are here, your st will be this, which will be different from this st. So, but for these different st's, you sum them up, and that gives you this area. And the area under this curve is the integral, it is also the distance. So distance is the integral, this integral. And when these, when you make the intervals smaller and smaller, and this is a basic idea of integral calculus, and this is where like really calculus differs from the algebra you have learned till now, is the idea of infinitesimals. Like when you get smaller and smaller intervals, your approximation becomes more and more accurate. Now that's just something which you should accept. When you get to, if you get to higher mathematics, or you get in depth, you can actually prove it. That you can start with the axioms and you can prove that really happens. But for you, it is sufficient to know, just sufficient to believe me at this time, that as the intervals get smaller and smaller, this approximation for the area gets better and better. And at the limit, now that's another calculus concept, at the limit meaning like when the intervals are as small as you wish and even smaller, then at the limit it actually is the area. It's the actual area. There's an equal to sign, okay? And the way that is expressed is that the sigma sign is removed in integral calculus. Instead, a stylized s is put instead of the sigma. Now, sigma is the Greek letter s, so you just put a stylized s instead, and you say lower limit of t equal to 0 to upper limit of t equal to 4 st dt equal to distance traveled from 0 to 4. So that's the integral calculus representation. Distance traveled from time 0 to time t, time 4 is this integral sign t equal to 0 to 4 st dt, and that is actually the distance traveled from 0 to 4. So that is, of course, the starting point of integral calculus. The next thing that you would like to know is at a later point, this is not all of integral calculus, this is kind of the introduction to it. The later point, what you would also like to know is if you can actually get analytical solutions, closed form solutions for this expression. And we are going to discuss that in detail as we go along. So in integral calculus notation, distance is now this is the notation for integral, and you can see it's actually kind of like a stylized s. So this is the integral notation. Distance equals traveled at time t from time 0 equals the integral of speed into distance. Just to recap, what we said is that if this is the speed, then you take a little piece, and this is dt, and the speed here is approximated to be about st. Now, of course, if the period begins at t, then the speed at the beginning of the period would be st, and at the end of the period it would be st plus dt, because the end of the period time is t plus dt, because the length of the time interval is dt. However, we just approximate and say that okay, it's just equal to st. And like I said, what integral calculus says is that as these time periods get smaller and smaller and smaller, and you have all these little elements which are really small, 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 and you add up the area of all these little elements, and each of these little elements have a area equal to st dt, and this integral sign is basically saying that you're adding them up, and you start from time t equal to 0, you start from here, and you go at till time t equal to capital T. So when you do that, then that total, the sum of all that area of these little elements becomes the total distance traveled. And so that's integral calculus. So that's the first part of it. It says it equals, not just approximate, it's a valid approximation, and it's actually completely true approximation in the sense that it actually is equal. And then what we would like to do in integral calculus is that we would like to get rid of the summation. We would really want to know, because it's okay, it's nice to know that distance is that, but if I have to sit and break it graph into little pieces and add them up, that's going to be very tedious. What we would really like is that when we have a formula like this, we would like it to be able to remove this integral sign and have a closed form solution. Now, of course, distance is not the only time when you apply integral calculus. Very few things in nature are actually constant. So whenever you want to multiply two things in nature, usually you have to resort to integral calculus rather than straightforward multiplication. For example, like take the volume of a sphere. Now, volume is, if you had a cube or a surface or a object with a rectangular base, then volume simply would be the area of the base into height. However, for a sphere, it is not constant, the cross-sectional area. So you can't apply the usual volume formula for it. Now this is really an onion, but I'm just, for illustration, I'm just saying that, okay, think that it's a sphere. Okay, so how does integral calculus allow us to calculate the volume of this sphere? Well, the first thing that we need is, okay, if you have a sphere, what is the surface area? And for that, the formula, let's say we know the formula, and it's 4 pi r squared, or let's say it is AR. So that's the area is the function, and it depends on R. The actual formula is AR equals to 4 pi r squared. So we know that a sphere with a radius r has a surface area equal to 4 pi r squared, okay, or as we represented by AR here. So how can we get from the surface area to the volume of the sphere? So what you do is you think of the sphere as being composed of thin hollow spheres. Okay, so for example, this sphere is made of an outer sphere and an inner sphere, right? Now, we know the volume of this outer sphere. Again, applying the idea similar to what we were doing with distance, is that we say, okay, this outer sphere has an outer surface area and an inner surface area which are quite close. And then the volume of this outer sphere would then become equal to the area, the surface area multiplied by its thickness. And the thickness is dr. So here we are integrating over the radius. For distance we were integrating over time. Here we are integrating over radius. So this outer sphere, which is hollow, it's hollow inside, and it encloses this smaller inner spheres. So this is a solid sphere, this is a hollow sphere. This hollow sphere encloses this solid sphere, and the volume of this hollow sphere is the surface area AR multiplied by its thickness, which is the dr, which is the radius change. So if you originally started with the radius to be, let's say, capital R, then now the remaining solid sphere has a radius equal to R minus capital R minus the small dr. Okay. Of course, now this solid sphere can again be thought as being composed of another hollow sphere and a smaller remaining solid sphere. So this is the smaller remaining solid sphere, and this is I wish I had 3 hands right now. Okay, and this is another hollow sphere which encloses this smaller, still smaller solid sphere. And the volume of this hollow sphere now is again its area, surface area, which is going to be a bit less than the largest hollow sphere which we earlier had, because this has a smaller radius. So it's going to be the surface area of this again into dr, and so on. And you think of like, so basically you look at the onion and you can see that, you know, it has many hollow spheres which all together compose the solid sphere. So the volume of the solid sphere is the integral, is the summation of the volumes of the hollow spheres. And what is the volume of each hollow sphere? Well, the volume of each hollow sphere is the surface area of that hollow sphere into dr, because dr is the thickness, right? So therefore the volume of the solid sphere becomes the sum of the hollow spheres, and each hollow sphere encloses the remaining spheres, and then you kind of integrate from r equal to 0. So that's like the tiniest, littlest hollow sphere right at the center of the sphere, and you go out till you get to capital R, which is the radius of the whole sphere that you started out with. So integral calculus then gives you the volume of the solid sphere. If you know what the surface area of a sphere is. So here's another application of integral calculus, and like I said, there's, you know, infinite number of applications, almost infinite number of applications, because things in nature are not constant, they keep changing, and you often want to multiply stuff in nature, and when the stuff is changing, you break it up into little parts. So you assume that like over the little period of time, or the little radius, or little whatever, the stuff is constant, and then you multiply it, and then you have to sum it up, and that's integral calculus. So here is one more example of where you can use integral calculus. Here we have the amount of water which has evaporated, let's say, from a container, equals the rate of evaporation multiplied by time. And if you are in, like, let's say, in a room, and as water evaporates, the humidity of the room will increase, which will impact the rate of evaporation. The rate of evaporation is going to fall. So you just can't say that, okay, the water evaporates for 1 hour and the rate of evaporation is half gallon per hour, and therefore the amount of water which evaporated is half gallon. You can't do that simple multiplication, because the rate of evaporation is changing through time. So the way you would do it is, so here what you're basically seeing is that the humidity is rising with time and the rate of evaporation is falling. So to figure out how much water evaporated during this time, you will have to take small intervals of time, dt, when you can assume that the rate of evaporation et is almost constant. So in the small interval of time, the amount of water evaporated would be et into dt, and then you would do an integral, which is a summation over the entire period of time, to get the total amount of water which has evaporated. So I have explained to you what an integral is. It is, basically the multiplication of two variables, and because they are variable, you need to multiply them in small pieces at a time. And then there is some that's integral calculus, and there are also some ideas about how accurate your approximation is as the pieces become smaller and smaller. Now, if I tell you, like, there is this integral, and I put something, some function st dt, now this is not yet something that you can really use. And this thing becomes much more useful. This becomes useful if you generally have a closed form solution. Sometimes if you just have an integral, you can break it up into small pieces and add them, which is the numerical integration. And of course, with computers becoming more powerful, numerical integration is much more feasible now than earlier. However, integration for many situations is really useful when you have a closed form solution. So what is a closed form solution? Well, a closed form solution, say, look at this integral here. So what you have here is that the distance from time t equal to 0.75 to time t equal to 3.2 of this speed. And so this is what the distance would be traveled from 0.75 to 3.2. And if I give you this, you still can't calculate the distance traveled, right? Okay, you can say, okay, I know that if this is the speed, then this should be the distance. However, you can't calculate the distance from this expression because there is this integral here, integral sign, and you don't know how to evaluate it. Now, a closed form solution would be when you can, if you're able to convert this into something which, let's say, looks like this, where distance with respect to time equal to some constant a into time squared plus b into time plus c. So this is what is called a closed form solution, because when you give me like the capital T, I can immediately tell you from here, I can immediately calculate what the distance was without doing numerical integration. So when you study integral calculus, you will, one of your major tasks always is going to be to find closed form solutions. You are unlikely ever to be told, or very unlikely to be told that, okay, go and find this integral, evaluate this integral numerically, write a computer program to evaluate this integral numerically. That is unlikely to happen. What is much more likely to happen, and what you'll find again and again and again, is that you'll be asked to evaluate integrals, which means to find closed form solutions. And we will get to closed form solutions, but first we have to study derivatives. So once we study derivatives and we understand the link between derivatives and integrals, we will be able to find closed form solutions for integrals. So, but we are still in only chapter 1, right? And we are just about maybe approaching the end of chapter 1. And before we get to closed form solutions, which is actually there in chapter 2, we need to understand differential calculus. So just like integral calculus is multiplying little bits and then adding them up, differential calculus is dividing little bits. Okay, it's like instantaneous rates of change, for example. So moving on to differential calculus. So differential calculus is about instantaneous rates of changes. So rates of change where the function, the change in a function for a very little change in the variable on which the function depends. For example, if you have distance, it will be about a very little change in distance divided by the corresponding very little change in time, which we normally think of as speed. So to give you some motivation for differential calculus, let's go back a few centuries, and probably the most important moment in human history was when Galileo, he rolled the ball down an inclined plane. So why did Galileo roll a ball down the inclined plane? Because when he just dropped the ball, it dropped too fast. He could not measure how fast it was dropping. So he thought of a way to slow it down, and he took an inclined plane and he rolled the ball down the inclined plane so you could have at least a rough idea of how much time it was elapsed for different amounts of distance traveled. Okay. So what did Galileo find? Well, he found, and here's a table, and it's not exactly what he found, but some kind of idealized form of what he found, that if you plot time against distance, so here it's time in seconds, and this is the distance which the ball has fallen, or it has traveled along the inclined plane, you get, as time passes by, distance seems to, greater distances traveled, and it seems to be traveled at a faster pace. So here is a table which kind of is what Galileo found, and next we are going to do a bit of processing on this table. So what if we looked at the difference in distance traveled for each second time interval? Well, in the first second, it was going to be 2.5 minus 0. In the second second, it is going to be 10 minus 2.5. So in the second time interval, the amount of distance traveled is 7.5, because the total distance traveled is 10, and at the end of the first second interval, the distance traveled was 2.5. So the total amount traveled in the second time interval is 7.5. In the third second time interval, the total distance after 3 seconds is 22.5, and out of which 10 was traveled in the first 2 seconds. So in the third second time interval, is going to 22.5 minus 10 is going to be 12.5. And similarly, in the fourth second, it was going to be 17.5, in the fifth second 22.5, and then the sixth second 27.5. Okay, so these are the different distances traveled in each second interval, from the first second interval to the second interval. So these are the distances traveled. Now you can see that like each second interval there's a greater amount traveled, and what is essentially happening is that the ball is picking up speed. Okay, so as it falls faster, then in each second interval it covers greater distance. So it's kind of interesting, but nothing earth-shaking as yet. Okay, so we're going to do a bit more processing on this. So now the distance traveled in each second interval you also call as speed, and what you are seeing was that the speed was increasing. The next processing that we do is to say that how much is the increase in speed for each second interval. And the first second interval you can't really talk about increase in speed because there was no prior speed to compare to, but in the second interval what we had was that the speed increased to 7.5 from 2.5. So the increase in speed was 5. What about the third second interval? Well, in the third second interval, the speed was 12.5, whereas in the second interval it was 7.5. So the increase in speed was again 5. Similarly, in the fourth second interval, the speed was 17.5, which is an increase of 5 over the speed at the third second interval. Similarly, for the fifth second interval, speed again increased by 5, and the sixth second interval, speed again increased by 5. Wow. So suddenly mankind realizes that there are mathematical relationships which govern the physical universe, and these physical relationships can be discovered by performing experiments. So this is the beginning of modern science and technology, and Galileo is called the father of modern science. So in this experiment, we discovered something which is true in nature, that is, the acceleration along an inclined plane is constant. And the other thing to note is that differences and rates at which differences occur are important. So you have a function, we were considering distance as a function, which is determined by the independent variable time, and we were looking at first the change in distance divided by the time over which that change occurred. So that was the ratio. And then we are looking at, so that ratio was speed, and then we are looking at the change in speed over the time over which that change in speed occurred, and that's acceleration, and we found that to be constant. So in nature there are many places where these ratios are important. So you have a function, you have an independent variable which determines the function. The ratio of the change in the function value divided by the change in the independent variable is important, just like we saw in Galileo's experiment, and often it has to be instantaneous. So we want that ratio to be calculated over a very little change in the independent variable. So it can be very little change in time, for example. So it can be like an instantaneous difference. And when you take that ratio and the change occurs over a very small period of time, it's called a derivative. Okay? And that's differential calculus. It is, you have a function, the ratio of the change in the value of the function to the value, the change in the value of the independent variable. That ratio is called the derivative, and that's differential calculus. Now there are particular names for different derivatives. For example, when you have distance and time, distance as the function and time as the independent variable, the derivative of distance with respect to time is called speed, and the derivative of speed with respect to time is called acceleration. And what we had found was that acceleration along the inclined plane is a constant of 5. So in calculus, the standard notation that we use for derivatives is of the form like dy by dx, where y is the function and x is the independent variable. For example, if you're thinking about speed, then it would be d of distance, which is the function, divided by dt. So here y is distance and x is time. So normally the notation is dy by dx, because the usual notation for the function is y and the independent variable is x. Another example of a derivative would be, let's say, the rate of flow of water into a bucket. And if the volume is Vt, then the derivative would be represented by d of V divided by d of T. And this is actually not a division, it's just notation. And that would be equal to the rate of flow of water, Ft. And why would we be interested in Ft? Well, we may be interested in Ft because it could be proportional to the current flowing through the water pump. Current flowing through the water, the square of the current flowing through the water pump determines the power of the water pump, and that could be proportional to the rate of water flowing into the bucket. Okay, so there can be various relationships in nature where derivatives enter. So having studied integration and differentiation, we want to know what exactly is the relationship between them. Now, integration is, like I said, multiplying little bits and adding them up. And differentiation is taking a little bit and then finding the ratio, so dividing little bits. So one is multiplying, the other is dividing, so they kind of seem to be inverse operations of each other, and indeed they are. They are indeed inverse operations, and that becomes very clear. When you look at, let's say, distance, speed, and acceleration. Now, you drop a ball, and like Newton says, the acceleration due to gravity is constant. So what is acceleration? Acceleration is rate of change of speed. So you differentiate speed, the rate of change of speed, which is the derivative of speed with respect to time. You differentiate speed and you get acceleration. Also, how do you find speed at a point? Well, speed at a point you find by seeing how much acceleration has occurred till that point. So you take acceleration over a little time period and you multiply that by the length of the time period, so you get the change of speed in that time period, and you add up all these little changes of speed to get speed at a point in time t. So speed is the integral of acceleration, and acceleration is the derivative of speed. Similarly, when you come to distance, what is speed with respect to distance? Well, speed is the derivative of distance with respect to time. It is the rate at which distance is changing with time. So you differentiate distance with respect to time and you get speed. And how do you calculate the amount of distance which has been traveled? Well, this is what we did initially when we started discussing integral calculus. I drew all these graphs of the journey from Los Angeles to Vegas, and I showed you how distance is the integral of speed with respect to time. So to calculate the distance you've traveled, you break up your journey into little bits, and the speed for each little bit you multiply by the length of time for that little bit, and then you add it all up. So you get distance from speed. So you integrate speed with respect to time, you get distance. So if I was to write out these relationships, I would have from acceleration to speed, the speed at any point in time, let me say that's st, would be equal to the integral of all the acceleration that has happened till that point in time with respect to t. So that would be the integral, let's say, time equal to 0 to time equal to, if this is capital T, you want to know what the speed at capital T is, and it would be the time from 0 to capital T of at dt, where at is acceleration at any point in time. This is the general formula for acceleration and speed. Acceleration does not need to be constant. For example, when you're driving a car, you sometimes accelerate, you sometimes deaccelerate. So acceleration keeps changing. And then you have, what remains true is that the speed at any point in time would be the integral of acceleration. Similarly, if you want to move from speed to acceleration, now acceleration is simply the rate of change of speed, how fast you are changing your speed. That's the common idea of acceleration. So your acceleration at is simply the derivative of speed st with respect to time. Similarly, when you want to move from speed to distance, you integrate, and that's how we started integral calculus. So you say that your distance dt equals the integral of time t equal to 0 to time t equal to capital T. If you want the distance traveled to time capital T, then it will be the integral from 0 to capital T of speed st into dt. So basically little bits of time dt multiplied by the speed, associated speed for that point in time. And when you want to move from, so this is moving from speed to distance, so that's how you get the distance. And if you want to find, so this is getting distance from speed. If you want to find speed from distance, that simply is st equals the derivative of distance with respect to time. And that's how we define speed, right? Speed is the rate of change of distance. When you say rate of change for, that is rate of change with time. So it is the rate of change of distance with respect to time. So here what you have is an illustration of how derivatives and integrals are reverse operations. And this is very important and useful because later what we are going to see is that we can find derivatives of functions analytically, what we also say from first principles. And then if we have a derivative of a function and we have derivatives for a set of functions, then we can guess what integrals of functions would be, because we know, for example, if I want to find out what this integral is, where the integral is st dt, I look for a function st equal to the derivative of dt, and then this function dt I know is that this integral over here. And that's what we are going to do in chapter 2. So now that we realize that integration and differentiation are reverse operations, we can actually use this idea to calculate integrals if we know some derivatives. For example, if you're looking to calculate this integral gx dx, we want to find this integral of this function. Now, suppose we represent this function by fx, right? So the integral of this function gx dx, and if we represent that by fx, then what we know is that the derivative of fx, dfx by dx, would equal gx. That's what we just discussed, that integration and differentiation are reverse operations. So if gx is the integral of fx, no. So if fx is the integral of gx, then gx is the derivative of fx. So now, given this, can we find, how do you find integrals? Well, to find integrals, what we look for is, if you have a expression like this to integrate, if you have like gx dx to integrate, what we look for is a function fx which on taking its derivative gives gx. And that fx then becomes the integral of gx dx. Now derivatives can actually be calculated analytically. Integrals can't, because in the integrals like adding little bits, that's not possible, but derivatives can be calculated from first principles. So this idea that integration and differentiation are reverse operations is used to find closed form solutions for integrals. Audio check, video check, take. Actually, if you have found a function fx which is on taking whose derivative you get gx, then the function, so this is, then the function fx plus c, its derivative will also be equal to gx, where c is a constant. Why? Because the derivative of a constant is 0. What is the rate of change of a constant with time or anything else? Well, you know, the word constant means no change, so the rate of change of a constant is 0. Derivative of a constant is therefore 0. So the derivative of fx is the same as the derivative of fx plus a constant, because the derivative of a constant is always 0. Therefore, if fx you say is the integral of gx, then fx plus c is also an integral of gx, because you said that fx was the derivative of, you said that fx was the integral of gx dx because it's this derivative of fx was equal to gx. But then, if that is true, if df by dx equal to gx, then it's also true that dfx plus c by dx is also equal to gx. So if this is the integral of this, then fx plus c must also be the integral of this. So basically what you have is that the integral of gx is fx plus c, and this c, which is a constant, if you take the integral between two limits, then the constant disappears, because the first limit, the upper limit you have plus constant, the lower limit you have minus constant, and you'll get to understand this as we study this more. So essentially what you have here, and just to recap, is that if gx equal to df by dx, then gx is also equal to d of fx plus c by dx, and therefore this amount fx plus c is the integral of gx dx. Stop. Audio check, video check, take. An integral which is written without the limits is an indefinite integral. You're just talking about integrating a particular function without really saying between what points the function is being integrated. Now this is a definite integral when you have the limits. For example, in this integral, you're integrating gx dx, and you're saying that you're integrating from the point where x equal to capital A to the point where x equal to capital B. Now when you do that, on the curve you can think, you can visualize it easily. You have a point x equal to A, and then the curve, you have the other point x equal to B, and you're integrating over this, you're trying to find the area of this between x equal to A and x equal to B. Now if you have the solution to the indefinite integral gx dx as being fb plus c, then the definite integral is the integral at this point x equal to A minus the integral at this point x equal to B. So no, actually it is the integral at x equal to B minus the integral at x equal to A. So that becomes now the integral gx dx was fb or fx plus c. So then the definite integral from A to B becomes fb plus c, that's the integral at this point, minus fa plus c, which is the integral at this point. Okay, so the c's cancel each other out, and what you are left as the value of this definite integral is fb minus fa. You remember for a sphere, for example, you are integrating from the point, if you want to find the volume of a sphere, then you are integrating from the point radius equal to 0 till the point radius equal to capital R, where capital R is the radius of the sphere. Similarly, you could have done a different definite integral. For example, you think of a sphere and then you think of a hollow portion within it. So if there's like the earth is a sphere, and then there is this, inside the earth there is a hollow portion within the earth, then you want to know what the volume of that sphere with a hollow center is. Then if this radius for the hollow portion is, let's say, radius equal to, for the hollow portion is h, and the radius for the entire sphere equal to, let's say, capital R, then your definite integral will be starting from radius r equal to h to r equal to capital R 4 pi r square dr, or that would be equal to the indefinite integral for 4 pi r square was 4 by 3 pi r cube plus a constant c, and you see the constant c's cancel each other out, so I'm just going to ignore the constant c. So it's going to be 4 by 3 pi capital R square minus the integral for r equal to h, which is 4 by 3 pi h cube. Or this is simply you're saying that the volume of that hollow sphere is the volume of a complete sphere 4/3 pi r cube minus the volume of a sphere inside with a radius of capital H. So for definite integrals which are within two limits, you have the value equal to f upper limit minus f lower limit, where f is a function which equals integral gx dx, or alternatively gx equal to the derivative of fx.